Okay, recording. I don't know if that moved. Okay. Let's see if I can close that. Okay, guys, can y'all hear me, see me? I'm seeing very few microphones and even less cameras by your names.
I can hear you now, and we can see you as well.
Okay, thank you, Jacavians. I'm going to go ahead and get started over again. So let me see. I may not. Maybe when I share this PowerPoint, it's messing us up. I'm not. It worked fine last night, so I'm not quite sure what happened. You're sharing your PowerPoint. That's what I want. I want this to go away. I want that to go away.
Maybe that's what messing up the bandwidth or something. I don't know.
Meeting recording, it's in progress. Okay, guys. Again, on page 674, we're going to quickly talk about the development of fluoroscopy. If everyone will mute your mics, hopefully that will help out. I was thinking about, when the X-rays were actually being discovered by accident by Dr. Röntgen. That was in 1895, and it was because he actually had a glass plate, a piece of glass coated with platinum barium cyanide, I believe it was. And he was working with electricity, and he was working with a vacuum tube. And as he turned this tube on, he noticed in the corner of his lab, something was glowing this yellow-green light. That was the very first time fluoroscopy occurred, or fluoro occurred, I should say. So going into the chapter, we talk about that. It talks about how he was discovered, and then a year later, in 1896, Thomas Edison actually created the first fluoroscope. Now, the one thing with the fluoroscope, is there still a little picture hanging over anywhere on my PowerPoint? Is anyone?
Yes,
Sir?
Yes, I see it.
I mean, but is there anything obstructing my PowerPoint?
No.
Okay, good. So the one thing that was about fluoroscopy, they used the word dynamic, meaning moving, or actually it's images in real time, kind of like you're watching television in real time, like the news and things like that, and not a movie that's been pre-recorded. So dynamic means that we're able to actually see inside the human body and see the actual organs do their functioning, the physiology of the body actually working. So that was the difference between a image that we create in diagnostic is called a static image versus a a fluoroscopy image, which is going to be actually a live image. It's a live, like you're making a mini movie of the person's anatomy. Well, with the setup that they have on this PowerPoint here, you can see that triangular tube at the bottom of it, right above the patient's hand. There is a fluorescent screen, just like the one that Dr. Röntgen had in his office. It's a glass plate coated with the fluorescent material. But the problem with this is that the doctor is looking directly over the patient's hand through the fluoroscopic screen to see this very dim image of the bones of that person's hand. And I believe that's Clarence Alley. But the tube itself is directly underneath that box. So in essence, the radiologist is looking directly into a live beam. So we all know that that's not the best setup. So obviously that's a very dangerous thing to have happen there. So we had to come up with something else to take care of this. And I think in your book it talks about the very first one was in 1940, was the image intensifier. Remember, this is a very dim image that they're looking at. Radiologists actually had to do the what they call dark room eye adaptation, where they had to sit in a room for a certain period of time. So when they came out, their eyes were adapted to the darkness so they could actually see even better of that dim image. Okay? So the original fluoroscope consisted of a metal cone. You just saw that with the fluorescent screen in the bottom and a viewing window at the top. And here again, there's a picture of one of the the older ones. Okay, the fluoroscope with the X-ray tube on the opposite side of the anatomy. You see where the arrow is. Can't get rid of this little picture on my screen, and I don't know why. The image carried by the remnant beam would make the fluorescent screen glow. We've talked about that. Okay, so the open fluoroscope, a large intensifying screen. This is pretty interesting here. A large image intensifying screen, that is it right here. It's this plate behind the patient. That's a screen, the glass plate, just like what was on that scope that Thomas Edison created. This is a glass plate coated with a fluorescent material. And here's your open, look at the tube, it's open. Okay, it was positioned behind the patient in a completely darkened room. The radiologist had to adapt their eyes to view the very dim image, which I said that earlier. Exposure to both the patient and the radiologist, whose head was directly in the remnant X-ray beam, was high. Well, of course, this is not the ideal situation. If you see where my little red cursor's going, here's the bulb. Here's the vacuum part of the bulb, the tube, going through the patient, hitting, just making this screen glow, but the X-rays are still coming through it. So that's a huge problem there, and that's when they started realizing the dangers of being directly exposed to radiation. I mean, no filters or anything to protect themselves, no lead. They were unaware of the dangers that this was really causing. So exposure to the patient and the radiologist, again, were very, very high. So in the 1940s, John Coltman was the first to create what we now know as the image intensifying tube. This is a tube that was designed to take that dim image, that yellow-green glow, and to amplify it to create a much brighter image. And that's what the second part of this lecture is going to be about. But what this intensifying tube's main purpose was to get the radiologist their head out of the viewing and being completely exposed by a live beam. But the principles of the electronic image intensifier is that it's converting that very, very weak remnant X-ray beam. We all know that there's only 1% of your primary beam that's responsible for image production. Well, this is still holding true way back there in the 1940s. So they're going to take that very weak remnant X-ray beam, and we're going to convert it into electrons that we can accelerate and focus them for a brighter intensification. And doesn't that sound very familiar to what the actual X-ray tube did? It took electrons, it accelerated and focused them onto a anode plate, so that they're very similar in nature of what they do. But of course, one is producing X-rays, the other one is taking those X-rays and amplifying their ability to create a brighter image. But with the introduction of the II, as we call it, the image intensifier, or actually in the clinical area, they're going to call it the fluoro tower. With the production or introduction of it, the patient dose was dramatically reduced. Your EMA is running somewhere like 2 to 5 EMA, which is very, very low. So that is definitely going to be saving your patient dose. Okay, the first II was only 8 centimeters in diameter, and modern II tubes can be up to 40 centimeters. And I want to bring this to your attention here. This big, huge thing here, all of this right here, this is the fluoro tower. Just like what Dr. Haynes showed you on the opposite end of the C-arm, this is the same tube. And this is placed over the patient. Notice there's a tube over here in the back. This one is parked in the very far corner of the room. So this one here has nothing to do with the fluoroscopy. There's another one mounted directly underneath the table, underneath the entire carriage, the whole table itself, and it's connected to this fluoro tower. So as you're moving the fluoro tower underneath the table, the tube is staying connected to it and moving in sync with it. But the first II tube, what you want to take away from this slide, is that it was only 8 centimeters or 3 inches in diameter. Through the process of experimenting with it, it was understood that if we created the circumference of this input phosphor down here to a much larger area, we would even gain more brightness. So today's tubes now can be as large as 40 centimeters or 16 inches in diameter compared to this little 3-inch diameter that the very first one had. Okay, the fluoro tower, again, I said, there's several recording devices. Right here, they're showing a white arrow with a camera connected to it. But this lecture and the next two will stop at this point right here when we start talking about it being coupled to some type of viewing device, whether it's a camera taking actual little spot films, which I did as a technologist, or if it's being sent directly to a viewing monitor. So we'll talk about that in physics too, but it has that output from your output phosphor, which is a tremendous amount of white light. If that's going to have to be collected and sent over, and we talked about, it has to be digitized also. It has to be converted over to a language that a digital system can read. So we'll talk about, the ADC, analog to digital converter. We'll talk about CCDs. But right now, again, we're concentrating on this big tower right here and why it was introduced into the imaging profession. So your fluoroscopic exposure rate, the X-ray generator requires additional circuitry to operate in the fluoroscopic mode, including something called an automatic brightness control. We will talk about that at the end in the third PowerPoint, the WebEx link that I posted last night. That's what I talk about is the automatic brightness control. Due to the low exposure rate, fluoroscopic images are statistically inferior to the overhead images and demonstrate more noise, and this is on page 675, due to low exposure rate. Now that is talking about the exposure rate to the input phosphor. We know that it's a low exposure rate. Someone has a microphone on. If I could please mute it. But remember now, we do use a very low MA during fluoroscopy, but it's the accumulation of the total time of a live beam, which can be up to 5 minutes plus, that now we understand that MA times 5 full minutes is going to give you a substantial amount of exposure. So fluoroscopy is where the majority of you being a technologist, your exposure is going to be coming from doing fluoroscopy, C-arm, surgery, anywhere where there's an image intensifier, because of a live image being kept on the screen, like I said, for up to 5, 10, 15 minutes. The accumulation of the total exposure is tremendous. So again, fluoroscopy is your primary source of exposure. And it's because of the time that the live beam is on, not that it's using a high exposure rate because we're using a very low MA. We're using a low MA because we know that remnant beam is going to be able to go through that image intensifier, and that brightness is going to be able to be manipulated to be much brighter so we can keep that MA very, very low. Okay, automatic collimation adjusts the field to the proper size when the SID is changed. This is on page 675. So as you change your SID, your collimators are automatically opening and closing to adjust to that change in SID. There is something called an automatic brightness control, the ABC, which again, we will talk about this. This is simply a process that is automatically done with the image intensifier. As the image gets lower, or the brightness gets lower because the patient thickness has increased, the system itself will automatically amp up the MA in order to maintain the brightness. So that's an automatic brightness control. And, there's multiple ways of doing it, but the one and the more prevalent is the manipulation or the increase in the MA. It tells you here there's other ways that it can be done. I think there's 4 different ways that you can actually increase brightness, but ABC is the more prevalent one in today's image intensifiers. It says the radiologist may select the brightness level desired, and that's just a push of a button on the control panel, and the ABC will maintain that brightness throughout the procedure. Okay, so that was the end. That was very short. That was part 2. Next, we're going to be talking about the discussion on the components. So I am going to pull up the next one. Let me stop sharing that one. And hopefully I can quickly find the next PowerPoint.
You've had a question.
Okay.
You may be covering it in the next part.
Yes.
Where's the output phosphor on the
Yes.
tower?
This was simply an introduction of what fluoroscopy is, how it was discovered, when it was discovered, and then when was the first image intensifier discovered. We will talk about all the parts if you haven't watched it, because you know the second video is all about this. So I'm kind of wondering if you didn't watch the second video, because that is exactly what it's all over. But we will get to that in just a second.
Well, see, I watched the video, but the way the output, the input is above the patient. So where would the output be? Was it on the side?
I'll show you that in just a second, Shacavius.
Okay.
It's coming up. All right, so I'm going to close this one out. And now I am going to open up this one. The slideshow from the beginning is, and now I need to end the show. I need to get back to this, and we're going to come over, and I want to share that screen. All right. Should pop up in just a second, and we do want to run this slideshow. So I need a minute.
There it is.
Yeah, but
that looks good.
Pause sharing will freeze to I want to go to my actual slide show from the beginning. All right, and I want my little pointer, my laser pointer, and I just wish this hide video view. I wonder what that's going to do. All right, I don't know. Okay, guys, this is the next part. This is actually talking about the image intensifying tube. This is on page 676. We're going to be talking strictly about the components of it, Shacavius. We're going to talk about what happens in each of the different layers and how we get that brightness, and that's going to be the third part of this presentation. So let's see if I can get it going. Okay, it says pause. What does pause mean? Paused. Oh, this is still recording.
I think it paused the recording.
Oh, it says it's still recording, and I want it to.
Okay.
What is that? Okay. So does everyone see my little pointer? Can't get the PowerPoint to advance. This is such a nightmare.
I don't see the pointer, but I see the.
You don't see the.
Wait, is it the white pointer?
No,
I see the pointer.
I got a little red thing on the screen right now. And y'all are not seeing.
I see the PowerPoint, but I don't see a red pointer.
Okay, it's not letting me advance my PowerPoint. Okay, here we go. Okay, so here we have the, this is on page 677, guys, in your book, figure 38.6. This is actually an image intensifying tube. And what we're looking at, Shacavius, this is our input. This is the side that's going to be closest to the patient. This is going to be the side down in that big tube housing. This is the big O circle. This is your input phosphor, which is going to collect the remnant beam. And then it will go through all of these different layers to get to this smaller one right here. This is called the output phosphor. Look how much smaller. It's 2.5 centimeters or 1 inch compared to this big, huge one can be as large as 40 centimeters. So this is the part that would have been connected to that camera or television or any type of viewing device. We're going to have a coupler here, and it will send that very, very bright, lot of light photons there. Okay, guys, I put this in there, and I struggled with this image. You can ask Dr. Haynes. I had everybody helping me out trying to figure out how to get this in there. But I thought this is really cool. I'm just going to run through it. Then we'll quickly talk about each one of these different components. But if you look here, we're dealing with one. This is only one X-ray.
Miss Kendall, we cannot see I cannot see what you're pointing at. And if you have changed the picture, I'm still stuck on the very first image you called up.
I'm looking at a schematic right now. Is everyone seeing that?
I think it's frozen for us right now.
Yeah, I don't see the schematic.
We still see the image intensifier that's slide number 2. There you go. There you go. That's it.
Are y'all good now? Did y'all see the one prior to that?
It's good now, yeah.
I see it now, and now I can see your red pointer.
Okay, it's still not letting me. Like I wanted to back up to the previous slide, and it's not letting me. This is really frustrating to me. But anyway, we're gonna get through this. Okay, so everybody sees this schematic. Everybody sees the little red pointer at the tip of the black arrow at the top. Does everyone see it?
Yes, sir.
All right. Yes, yes, yes. All right. So
can I add something real quick though, since I wasn't able to see it a second ago?
I'm sorry.
Just real quickly, the big like image intensifier tube, the one that's like big and round, that's the one that's closest to the patient and collects the remnant beam.
Right. I'm trying to back the PowerPoint up and it's not letting me do it.
Okay. Because I couldn't see what you were pointing to when you were talking about it. I just want to make sure I was on the right one.
Okay, well, that same slide is on page 677, figure 38-6. It tells you the photographs of the image intensifying tube showing the output phosphor. A is the tiny one. That's up here, right here. And then it says B is the input phosphor, and it is this big one down here. Your X-rays have to go through the input. It has to go in before it can go out. So input phosphor is right here. This input phosphor right in here. Okay? And your output phosphor. Okay, so we're going to go through this step by step. We're going to take one X-ray at 50 kilo electron volts. We're going to go through. Remember, this is that big round dome of glass. We're looking at it from the side right here. Okay, well, I'm sorry. I should start right here. This is your fluorescent screen. Fluorescent means that it's going to do what? Fluorescent means that it's going to glow light. It's going to take the energy of the X-ray and it's going to, from this little line right here, this coating or your fluorescent screen, it's going to take that energy of the electron, of the X-ray, and it's going to convert it to white light. For this representation, we're taking that one. Now we have 2,000 light photons in this area right here behind the fluorescent screen in a response to the energy of that one X-ray. So one X-ray now has become 2,000 light photons. The next layer that it has to go through is called a photocathode. So we know from the cathode, what do we get in an X-ray tube? Electrons. So it's going to take the photons, which are called light photons. It's going to take it's a photocathode. So it's taking light photons. Here we have the 2,000. It takes a lot because light photons are very weak. We're going to take those 2,000. We're going to push them through the photocathode, and we get 100 photoelectrons. Now we're in this area right here. So we've gone through 2 layers. We've gone through the fluorescent screen, and we've gone through the photocathode. Fluorescent screen and the photocathode, we went from X-rays out here to light photons. Now we have electrons. But notice we took one, we got 2,000. Then it took a lot of light photons because they're weak to release only 100 photoelectrons. So now you're dealing with what you're used to hearing about in an X-ray tube. We now have an electron stream. These electrons are being emitted in this entire area right here, your photocathode. Okay, 100 photoelectrons are going to go through, and as they're going through, they're picking up kinetic energy supplied to them by these things right here. They're called electrostatic lenses. And notice they get closer as you get further down towards the bottleneck of the image intensifying tube. Okay, the next thing we have, and I want to tell you, these have voltages applied to them, positive voltage applied, and it gets stronger as you get further up towards the bottleneck of the image intensifying tube. This right here is called your anode accelerating ring. It has, does someone have a question? This has 25,000 volts applied to it. So that's going, and it's positive. So it's pulling, it's attracting these, all of these have positive charges. So the positive charges are pushing these in, and this huge charge of 25,000 placed on the anode is pulling them up. So they're increasing an incredible amount of kinetic energy, just like in the X-ray tube. And then they're going to hit, after they go through the anode accelerating ring, it is a ring right here, they're going to go through what we call the output fluorescent screen made out of cesium iodide, just like the input phosphor down here. So it's taking the electron, the kinetic energy, that energy is going to be pushed through a fluorescent screen. When you push energy through anything fluorescent, it's going to glow. So we've got 200,000 light photons. So we went from 2,000 light photons down here from one X-ray to 200,000 light photons because of the increase in the kinetic energy provided by these positively charged electrostatic focusing lenses and the anode accelerating ring. Is there any questions?
Yes.
Okay.
Okay, my question is, okay, I'm trying to make sure I understand you correctly. Since the X-ray table is under the patient, the input is going to be at the bottom. The input phosphor is at the bottom on this tube. Is at the bottom. It goes up into the output, which will be on the top.
That's
and it's like standing straight up.
That's correct. Your patient is way down here. Shakavius, your patient is way down here. This is a remnant X-ray. Remember, we're shooting up. The X-ray tube is way down here. If you would think of it, it's way down here in the blue. Then your patient, this is remnant X-rays. So this is kind of like the upside down of what you're accustomed to thinking about in an actual diagnostic tube, where your tube would be at the top going through the patient and you have your plate underneath them. This is thinking of it upside down now. Your X-ray tube made the exposure down here. That's where we got the remnant X-ray beam after it came through the patient. And then it went through the input phosphor and it comes out of the output phosphor. Does that help? Does that help?
Yes, very much so, because that's what I was struggling with. Mm-hmm. I'm used to the patient coming down on the patient, and this time it's going over the patient.
Well, remember, Dr. Haynes talked about the C-arm, and where did she tell you the tube was located, and it was safer for all of us? It was underneath the what? Table. This is the same principle here, and you remember, look over on page 676. I showed you the image of the tower, and I told you there was an X-ray tube, and it's parked over there in the far corner. It's not even being used because there's another X-ray tube underneath the table that you use for fluoroscopy. So in a fluoro capability room, there's actually two X-ray tubes. One's connected to the carriage that's connected to this image intensifier, and the other one is the one that you're used to using for diagnostic X-rays. So yes, you're thinking of this in the opposite, because we're thinking of the X-rays coming down. Well, in this case, the X-rays are coming up from the actual tube placed underneath the table. I can't get my PowerPoint to advance. Click next to get it done. These are just other pictures I put in there, guys. It was for your purposes there. It says this is just a quick review here. It says let's review now, making sure everyone understands the parts and what occurs with each one of them. So as the X-ray photons, and I cannot get rid of this little square on my side. I don't know what to do with it. Okay. All right, let's review. It says X-ray photons strike the input phosphor and convert it into visible light. The light photons, we got what, 1,000 of them from that one X-ray, right? So now we've got white light, which we know has less energy than an X-ray. So now we're going to push those light photons, white light, through that photocathode. It's going to take the energy of those white light. It takes a lot of them just to release one X-ray. So we push it through the photocathode, and now we've got 100 electrons freed up. So those 100 electrons are now going to be pushed up and focused real tight, real condensed into the focal point, then through the accelerating anode, all because the electrostatic lenses and the anode all have positive charges placed on them. So they're going to be pulling all those freed electrons with a negative charge. They want to go towards that positive. So you have a weaker positive on the electrostatic ones closest to the input phosphor. As you get closer to the top of the tube, those focusing electrostatic lenses have greater charge, and then you have the anode ring itself with 25,000 volts of charge. So you can see the kinetic energy these electrons are building, and that kinetic energy is what's going to give us that huge burst of light as it goes, those electrons actually going through. It says passing through the anode hole and finally arriving at the output phosphor. It's only 1 inch in diameter, where the photoelectrons are converted back into visible light. And it said, looking at that picture that we were talking about, after interaction with the input phosphor creates 2,000 light photons, which after interactions with the photocathode produces 100 electrons, which after being focused and traveling across the tube, you're going up into the bottleneck with great energy, finally go through the anode and interact with the output phosphor, creating 200,000 light photons. Does everyone understand that? That is what this chapter was all about. Okay, so here is the image intensifier, the round glass, the big circular diameter. That is your entire input phosphor. It converts the remnant radiation beam into an amplified light signal. So this is fluorescent. It's going to take the energy of the X-ray and it's going to emit white light. Okay, it says a large evacuated glass envelope or vacuum tube containing 5 electronic components. That's what is enclosed in this. It's available in diameters of 15, 23, 30, or 40 at the input phosphor shown here. So this can vary in dimension. The biggest one is your best because you got a larger surface area to collect the remnant X-ray beams. Okay, increasing the physical diameter of the input phosphor results in increased image resolution. So the larger your input phosphor is, the better resolution. Since a larger number of pixels are focused onto the same output size, remember, this little bitty output at the top is always going to be 2.5 centimeters or 1 inch. This can actually vary, and we'll talk about that in the next video talking about magnification. You can choose to use the entire surface, or you can choose to use any of the inner area. You can reduce the amount that you're using. Does anyone have any questions? Everybody good? Dr. Haynes, you with me? Okay.
I am here.
All right. Is it coming across okay?
Yes, it's coming. It's working good now.
All right. The input phosphor, again, this is just, we're just repeating it. I just thought that schematic at the front was really an easy way of looking at it because it gave you actual numbers. The input phosphor is a layer of fluorescent crystals called cesium iodide. It absorbs X-rays and it re-emits energy as yellow-green light. We know light has very weak energy. And the one thing that is important to understand why we've chosen cesium iodide how they actually create the input phosphor lens, it's sprayed on. And as they spray this cesium iodide on, it has a tendency to create needle-like projections. They're hollow needle-like projections. So as they are being activated by the X-rays, they're giving off light, but because of their own shape, they're funneling that light and preventing that light from being dispersed laterally. There's a name for it. I cannot think of that deposition of the as it's spraying on there and it grows. But anyway, the reason they chose cesium iodide was that it had a unique feature. As they sprayed multiple layers onto this input phosphorus, actually a sheet of glass, curved sheet of glass, as they sprayed it on there, as it accumulated, it started forming needle-like projections, crystals of fluorescent material, but they were hollow, needle-like projections. So as they gave off light, that light was being created or prevented from dispersing because it was being contained within its own needle-like projection. So it prevented that lateral dispersion of the light. That would be a good test question right there. Why was cesium iodide chosen? And here's your answer right here. Because that it's needle-like projection when it's painted on the surface of the glass input phosphor, and it helps to prevent lateral dispersion. Okay, the photocathode. Photocathode. We know that the cathode is able to give off electrons, the same thing as in an X-ray tube. Photo meaning those yellow-green light photons. So a thin photoemissive metal layer made out of a combination of antimony and cesium compound. This is your photocathode. Remember, right between these two layers is where your yellow-green light is at right now. So now it's fixing to go through the photocathode. It's going to take those light photons, and it takes a lot of them because they have weak energy. It's going to go through this, and it's going to release an electron. Upon absorbing light energy, it emits electrons. Thus, a beam of millions of electrons is being produced. And the unique thing is, look how spread out they are here. And look how tight they are here. That is what we're after. That is that I want to say it's called minification gain, but your book gave us a different definition. We'll talk about that in a minute. But what you're doing, you're condensing and you're forcing all of these electrons to get closer and closer to each other, and you're forcing them to go through a very small 1-inch diameter, whereas they actually come from this big old 40-inch circle of fluorescent and photocathode material. Okay, the electrostatic focusing lenses are these right here. Each one of them carries a voltage, and that voltage does increase as they get closer to your anode accelerating ring right here. Okay, and there's a positive charge. Well, all this electron beam has negative charge, so they're being pushed. This is very great. It says a series of positively charged metal rings that become narrow towards the anode end of the tube. Stronger positive charge on each narrower ring focuses the electron beam onto the output phosphor. Concentrating the electrons increases output intensity, and this process is called minification. You need to know that word. It's going to become important. So minification simply means you're taking this long, broad area here, and you're forcing it to be pushed through this tiny little opening of the output phosphor. So that is called minification. They're so tightly wound or condensed right here that it's minification, but they're extremely strong. But they're just compressed and condensed because of the high voltage, both from the electrostatic lenses and, as we'll see in the next slide, your anode accelerating ring. Any questions? Okay, here's your accelerating anode. It's a small ring of metal in the neck of the tube with 25 to 30,000 volts of positive charge applied to it. So you can imagine what that's going to do at this point right here. The electrons are already getting very, very tight. Once they are pushed through this anode ring, they're being pushed against 25 to 30,000 volts, so they get very, very tight. result in acceleration of the electrons in parts 50 to 75 times the kinetic energy they started with. Remember, these here are each having voltage, and these are called accelerating electrostatic accelerating rings, and this is called an accelerating anode, because all the point of these right here and the anode are to accelerate the electrons. The electrons are going to gain kinetic energy because of that high voltage applied to your electrostatic lenses and to your accelerating anode. It's going to be the kinetic energy that the electrons are carrying that's going to give us that brightness over here that we're looking for. Okay? It says this gain in flux or flow, it's called influx or flux. This gain in flow or flux gain also increases output intensity. All right. So all they're telling you is that the flow of these electrons as they gain kinetic energy, that is called your flow or your flux gain. And your book has a different definition for it, and I kind of agree with the book, but we'll talk about that in our next section. But just keep in mind that the point of the focusing lenses and your accelerating anode is to force these electrons that are really spread out right now, they're dispersed. You're going to force them closer and closer together to the point right here where they're just almost solid right here because they're so condensed. And that's what we're fixing to do. We had to get them condensed because we want to get all this information these electrons have of your remnant beam. We want all that information to be displayed over here on our monitor. But we have to get it through this output, this tiny output screen. So the increase in kinetic energy is going to allow us a huge response when it goes through this second glow at the top of your image intensifier. You're going to get a substantial increase in the amount of light given off. And then again, like I said, we will talk about what happens with that light in physics too. But you need to understand the process of the image intensifying tower itself. Okay? The output phosphor is again made of cesium iodide, converts the great kinetic energy of the electron, striking it into light. And again, this light is then going to be picked up by either a charge coupler device or a complementary metal. I can't think of what I had it on. Complementary metal oxide. Can't think of the S. I went completely blank right now, and I had made a note of it. Anyway, it's a type of camera. God, that kills me. I can't think of that right now. I'll get it. All right. So anyway, that's going to actually be in physics too. But I wanted to let you know that at this point right here, this 1-inch diameter output phosphor has to be coupled to something that is going to be able to take that signal now that is white light and do something with it so that that white light will then be converted to an image that will be able to be displayed on an actual monitor, okay, or a camera like you saw on that other slide. All right, God, that was the end of that one. Let me see if I can pull up the next one. And we're still going sharing from the beginning. And my pointer is gone. Pointer, I'll let my laser pointer. Brightness gain. Are y'all still seeing this? Dr. Haynes?
Yes, sir. I see it. Looks good.
All right, so we're on our third PowerPoint, guys. These are all broken down into mini WebEx YouTube videos. So now that we understand the image intensifying tube, it says now we will discuss how much brighter the images actually are when the remnant beam has gone through the image intensifier. Okay, brightness gain in itself, and I believe this is only a couple pages. This starts on page 678 under the category brightness gain. Minification. The concentration of electrons onto the output phosphor, which is much smaller than the input phosphor. That is the definition of minification gain. Minification is part of the brightness gain. There's two things that create brightness gain, and one of them is minification gain. And we talked about how you take that large input phosphor, you're pushing all of that through that small output phosphor, and it says it's measured as a ratio of the input phosphor, the area, to the output phosphor. And there's a formula for a circle, and everyone should know this. It's pi times radius squared. And your radius is always going to be half the diameter of a circle. So the area is 30 centimeter for your input. The area for your output phosphor is 2.5. So you put it through the formula. You're going to get 3.14 is pi. Half of to look for the radius, you take half of the total circumference of the circle, which is 15. You square that, multiply it by 3.14, you get 706. The area of the small one is 2.5. You want the radius, which is 1.25 or half of it. Multiply that times pi or 3.1, and you got 4.9. We're going to round that up to 5, which is what we've done here. So just through the process of using a large input phosphor and pushing all that information all the way through those different layers to get to that output phosphor, we have now caused the image to be 141 more times brighter. And that is just through the process of minification. There's two things that go along with brightness gain, and this is the first one. Does anyone have any questions? This is minification gain. Simply using a large output and a large input and a small output, and forcing those electrons real tight. Is there a question? Okay, brightness gain. This is where I was a little confused on it. How the book talked about it. Let me find it for you. Okay, on page 678, and we talked about flux gain or flow gain in relation to that kinetic energy being created or given to those electrons as they were being accelerated towards the other end of the tube, which is at the cathode end. No, from the cathode end to the anode end, accelerating the anode to the output phosphor. We said that was the flow, how the flow was getting greater and greater. They were getting faster and faster. And it defined it as flux gain or flow gain. Well, in your book on page 678, in the very top of the first column, it says the ratio of the number of light photons emitted by the output phosphor to the number of X-rays striking the input phosphor is called flux gain. I like that definition more so than I like the one on this PowerPoint. They were both provided. This came with the book. But I was reading this last night, and I was like, I understand this is what causes the change in the X-rays, the few X-rays, and then you have a lot of light at the other end of the image intensifier. But I do like the ratio of light photons emitted at the end of the process in relation to the incoming X-rays. So I do like that definition on page 678 at the top of the first column there. So I would want you to understand the one that is in the PowerPoint, because without this, and the one thing that you can't do, you're never going to be able to calculate flux or flow gain, because we have no idea how many are in our remnant X-ray beam. That's billions of X-rays, even though we say it's a few of them in the remnant beam. And we don't know how many light photons are coming out of the output phosphor, or that 1-inch output phosphor. So there's really no way that you're going to calculate that. But in any given problem, and no, we will not be calculating it. So don't worry about that. But if you happen to be reading your book, they always give you the flux gain as an actual number. They don't tell you how many X-rays went in and how many light photons come out, and you have to calculate it. And then it says the minification gain. We know how to get that. We just did the formula on the previous slide. But for these two numbers, with your flux gain of 70 and your minification gain at 64, your overall brightness factor is 4,480. So you can see that the image intensifier is doing an incredible good job at causing that image to become so much brighter. And it says typically the brightness gain ranges from 5,000 to 20,000 times brighter. And it says the overall brightness gain is the product of minification gain times flux gain. You need to know definitions. You need to know flux gain. I would like for you to know the definition in the book on page 678, as well as understand this process by definition here too. Flux gain couldn't have happened if we didn't have that increase in kinetic energy. You would have nothing. The electrons would not be accelerating to get to that output phosphorus. So I understand that the acceleration part is actually what causes the flow to increase. That's why I can relate to this definition, because flow to me means accelerate, to move. So what's causing the electrons to move is actually those electrostatic focusing lenses and that accelerating anode. Does anyone have any questions?
No, sir.
I do, real
Doing
quick.
great.
Did I hear a question?
So you said, yes, sir. So I just wanted to clarify. You said that the gain of kinetic energy is coming from the high voltage that's being applied to the electrostatic lenses and the accelerating anode.
Correct. That's what.
Okay, thank you.
That's what's causing them to have that that movement. They're picking up kinetic energy because they're being pushed through a big. These lenses are actually rings around the whole tube. So as the electrons go through, they're feeling this huge positive charges on the outside. So they're pushing in, pushing in, pushing in. And then when you get to that bottleneck of the image intensifier, you have that accelerating. Listen to that. It's called accelerating anode. So it's got 25,000 volts on it or more. So you can see all of them are really going to be pushed down into that bottleneck. So they're picking up even more kinetic energy as they go through the accelerating anode. So your electrostatic lenses is actually helping to accelerate and focus. And then once they get through the accelerating anode, they're exposed to a huge amount of voltage, up to 25,000. So both of those processes are causing those electrons to speed up with kinetic energy. And it's the kinetic energy, just like in the X-ray tube. Remember, as we applied our KVP, that was that push that gave those electrons that kinetic energy needed to slam into the anode, the tungsten material in the anode, to create X-rays. So it's kind of along that same idea here. Does that help out, Lainey?
Yes, sir. Thank you.
You're welcome. All right. Next thing we're going to be talking about multi-field tubes and magnification modes. The only thing this tells us, and I want to think about the image on page 677 one more time. It says the field of view, the specification of the active diameter of the input phosphor. A large field of view allows more anatomy to be viewed with less panning. Panning is simply a process. When we talk about we're panning the patient, we take that huge tower, we pull it over the patient, and we start moving it around to look at like if we're following the barrier, we'll start up there at the pylorus, which is the upper portion of the stomach, the esophageal junction. We can even watch it go down the esophagus, then we pan down, we watch it go into the stomach, then we follow it coming out of the into the duodenum, and that's called panning. But if you're using a large field of view, which means you're using the entire input phosphor, the whole screen, the big 40 inches, whatever it is, you're using all of it, you have a larger field of view. You're seeing more anatomy. So you have to do less panning. Okay, if you're, as you were going to get into our magnification mode, which is what this is coming into being, you're going to be seeing less anatomy, but because, or using less of the input phosphor. So instead of 40, we're going to say, I'm just going to use a number. We're using half of it. Now we're only using 20% from the center out, 20 inches of the 40. We're only using half of it. So we're only seeing half the amount of anatomy. So our field of view is now smaller. And because of that, we're going to have to, well, I don't want to jump the gun to get into the magnification mode, but the multi-field tubes simply tell you that on the control panel, there's 3 buttons, and it's going to have, I'm just using numbers, 40 for full diameter of the input phosphor, meaning you're going to see lots of anatomy. You're going to have 20, which is using half of it. So your field of view has gone down by half, or 10, which you're going to see very, very little of the anatomy. So that's called a multi-field tube. You're able to use different parts of the input phosphor depending on what you want to do, whether you want to see all of the anatomy, less of it, or you want to mag down to a specific part. So it says magnification mode reduces the field of view. You're reducing the amount of active material on the input phosphor. So you're not using all of it. So what do you think that's going to do to the overall brightness versus the whole input phosphor? Now we're only using half of it. Are we going to get as much brightness as if we were using the whole input phosphor? What do you think is going to happen? Anybody? If you got 20 inches of input phosphor, now 40, the whole circle. Now we're down to 20. We're using the central part, 20 inches of it. Your brightness will be cut in half because you're only activating half of the input phosphor. So brightness will go down as you're changing your field of view, as you're changing and using less and less of the input phosphor. The amount of brightness will go down because you have less X-rays interacting, right? That's the reason right there. You have less, everything is less now because your input, you didn't have the full field of view where all the X-rays of the remnant beam are being used. Now you're using less of them. So the reactions or interactions between each level reduces. So at the very end of the output phosphor, you have less brightness, you have less light photons, simply because you're using a smaller field of view. Any questions? I know this can get a little hairy, guys. Any questions? So a multi-field tube simply tells us that it has, and they all do, it simply has the capability of either using, and one of the examples I talked about in the book, on page 679, first column, second paragraph, it says the magnification mode can be selected at the push of a button for image intensifying tubes with dual mode or tri-mode fields. For example, a tri-mode, the biggest is 23, then you can go down to 18, then you can actually even go down to 12 centimeters. Those are actually magnification modes. You're choosing less of the total input phosphor, so you're seeing less anatomy, okay, less anatomy. And the one thing we're losing when we do that, we're losing brightness because we have less of the active area being used. So less X-rays are actually being involved because the ones that are hitting the part that's not selected, it's not responding. So it's just a part that's active, that's activated, and that's what it's talking about, multi-field. It says since a smaller region of the anatomy is displayed on the same size monitor, the resulting image is magnified. So we've got a very small area that we're now calling the active area. We're going to use the middle number there in the book, 18. Instead of the 423, we're going to use 18. Well, those are going to go through the same process, the same lenses, the photocathode, the electrostatic lenses, and that small area of anatomy being viewed, smaller field of view, is now going to be spread out on the same size monitor as if you were using the whole input phosphor. So you have magnified the image. It's going to take up the whole entire monitor, so the image is now larger, but the downside is it is less bright. Does everybody get this? All right, multi-field tubes and magnification. Okay, does someone have a question?
No, I was just saying that I was just going to remind them that there's also multiple videos posted in Moodle. You know, if they need to see it in action, maybe that'll help. But that, yes, they need to know everything that you're going over. And personally, I feel like this is the most difficult content since the circuit. Out of the whole semester, these two topics are the most difficult. So you need to make sure you are understanding this.
Yes, please watch everything we post. Please watch it. Please, and ask questions, guys. Ask questions. This is really a good time for Q&A. Okay, so we understand magnification mode. It simply tells us that we're using, I got my little pointer here. Okay, I got my red pointer going again here. Look right here. Look, we're using the entire input phosphor. Notice right here, we're only using this portion of it. And the way this happens, we don't go in there and like black out part of the input phosphor. The way this happens is by moving the focal point. This is your focal point right here. And there's your focal point right here. Well, to get that focal point to move, we're actually able to apply even more voltage to both the electrostatic focusing lenses and the accelerating anode. So as they even get more energy applied against them, your focal point actually moves closer to your input phosphor as the voltage increases. So that's going to, when it gets closer, you're using less of the input phosphor because these now have higher voltage to them. Notice the distance here to the beam, it's gotten tighter. So they're getting tighter quicker. Now notice the difference right here from this first set of lenses, right? This distance right here, look how much it's increased. So yes, you are definitely going to be, you're definitely using less of this right here. Because when you go into, you're going into the magnification mode, you're going to go push the button and it says 18 centimeters. It automatically increases the voltage to these right here, your lenses and your accelerating anode, and it pushes them. So the only thing that is activated now is this central part, and we're going to call that the 18. Yeah, this is the 18 centimeters of the total of the 23. So we're using less of the input phosphor, so less of the photocathode. So yes, everything is less here. So there's going to be less electrons in here. Okay, but the good thing about it, the reason you're doing that is that now this here has been magnified because you had a smaller field of view. So just this amount of information is now going to be displayed on the same size monitor. We're not going to use just the middle portion of the monitor. It's going to be the whole monitor. So you have more pixels involved to demonstrate less anatomy. So less anatomy, smaller field of view is going to be displayed on the same size monitor, but it's going to be blown up because you can now put more pixels, and that improves spatial resolution. You get better detail in magnification mode. That's the plus side. So for magnification mode, you got better resolution, you better detail, you're able to see things better, but the actual image has gone down. The brightness of the image has gone down. Okay, so it said by moving the focal point of the electron beam closer to the input phosphor, This is your input phosphor. Here's your focal point. It says a smaller region of the input phosphor is projected onto the output. So this now is the smaller amount being projected on the same size output phosphor. Any questions on this? So for the magnification mode, you're going to get a dimmer image, but you get better detail. You're seeing less because you're reducing the field of view. You're using less of the input phosphor as a total. You're not using all of it. You're using the 18 inches. This is the 23, but we're using the first step of magnification. So we're going to say this is 18. And guys, these numbers are hypothetical. Don't memorize them. Just know that for magnification, we're using less here. But upside, the plus side is better, less anatomy. Means we're getting it magnified. We're able to see better detail, but there's less brightness. That's the downside. Now, how do we correct that? Well, there's something called, I think I mentioned it earlier, called an ABC, automatic brightness control. And remember, the doctor has pushed a button and it wants that contrast, that brightness to stay on that monitor at all times. So the machine works with you. And as the magnification mode has caused the signal and all to be weaker, less electrons, less output, it's going to amp up your MA. And your MA, remember, is underneath with the X-ray tube itself, exposure. So by amping up your MA, that's going to put more what? More X-rays in the remnant beam, even though it's a smaller field of view. Well, we got more X-rays in here now because we put more milliamperage in there. Now we've got more electrons in this smaller area here. So you're getting brightness. You're gaining your brightness back by increasing your MA. Well, who's suffering from that? Higher MA means what in radiology? To the patient? What does it mean?
Exposure. Higher patient dose.
That's right. That's right. Higher patient dose. So when you're running your image intensifying tubes in the mag mode to overcome the brightness, the loss, I should say the loss of brightness, the machine automatically compensates by amping up the MA. Your patient exposure is going up. So the highest exposure that you can get during your patient can get during fluoroscopy is your smallest field of view. Because there's one step, we had the 23, we had the 18. If you were using the 12, it's really going to have to amp up that very dim image because you're using less of the input phosphor. Okay, dual mode or tri-mode intensifiers allow different magnification levels to be selected at the push of a button. I've already kind of mentioned that. Magnification mode can be used to improve spatial resolution or sharpness. There's the test question. What's the advantage of using magnification mode? You're seeing a smaller field of view. You're seeing less anatomy. And you can actually say that you have improved spatial resolution or sharpness in the image. The downfall of that is what? Loss of brightness. A smaller anatomical area is displayed with the same number of pixels available on the monitor. We didn't change the monitor. We did not change the monitor. The monitor is staying the same. Therefore, there are more pixels per area of the anatomy and smaller details can be made out. So because we're able to use more pixels to display less anatomy, that anatomy will be magnified on the monitor. Magnification mode produces a dimmer image. I've already said that about 10 times. You need to understand the process of why the image is dimmer. With a smaller input area, minification gain is lost. With a smaller input area, because what was minification? Minification was input diameter versus output diameter. Remember that equation. So obviously, if you're using less of the input phosphor, your minification gain goes down. Minification gain was part of your overall calculation for image brightness. Brightness gain was minification gain times flux gain. Was there a question? Okay, magnification mode and patient exposure. We're almost through, guys. Hang on. To avoid the appearance of noise from a poor SNR, SNR is signal to noise ratio, the automatic brightness control increases the MA to compensate for the loss of magnification gain. Patient exposure increases by the ratio of the change of the area of the active input phosphor change. So the smaller the input phosphor active area that we're using, the higher the patient ratio will go up, or patient exposure would go up. This can actually increase if you're using a 25 and you were changing from a 25 input phosphor to a 17 centimeter input phosphor for a smaller field of view. Just this change right here can cause your patient exposure to go up 3 to 4 times the normal exposure. Okay, does everybody understand we're talking about ABC? The automatic brightness control increases the MA because in your magnification mode, although you're seeing a smaller field of view, you're getting magnification, better detail, the image is dimmer. So the machine will actually increase your MA to compensate for the loss of your magnification gain. Magnification gain simply less bright. So you're going to have to get more patient exposure, and the exposure can be as high as 3 to 4 times higher than normal. And I'm going to stop there, guys. This is actually where we're going to pick up the types of ABS circuits. We don't really want to talk about those. They get a little bit more complicated. So I'm going to stop my recording. All right, guys, that was an hour and 11 minutes, so it's not too bad.